Hello, my name is Thorsten Schmidt. I'm a product marketing engineer at Power Integrations, and today I would like to introduce you to the SCALE-iFlex LT product family. This is extending the reach of our SCALE-iFlex products within the wind power industry. SCALE-iFlex LT is a flexible solution for wind applications, which is benefiting from the key features which we have in our SCALE-iFlex solution. So mechanically, it's providing the same design freedom, and electrically, it is achieving a very good current sharing between the different modules thanks to the very precise switching behavior. Now let's start with a deep dive on the SCALE-iFlex LT solution. So yeah, it is made for easy paralleling of those 17mm IGBT modules, also known from different vendors under different names, such as EconoDUAL 3, which is the Infineon name, or NX, which is the Mitsubishi name. And there are many more vendors in the market which are providing this certain form factor of power module. The key benefit for the customers when they use our solutions, where we can help the most, is we can clearly increase the utilization of the modules used. So we can increase the performance by approximately 20% compared to a conventional solution. So with our SCALE-iFlex LT solution, our customers can achieve the same converter output power by using less hardware. This is resulting from the very precise switching performance we are delivering, resulting in a very good symmetrical current sharing between the different connected power modules. So we are eliminating 1 out of 6 power modules compared to a conventional design, and we are therefore consequently helping to reduce the system complexity and costs related to modules. Of course, if you can spare one module, is significant. And further savings are based on wiring hardware such as the mechanical bus bars and the size and the length of the heatsink. So with our design, we are providing a mechanical freedom and high mechanical flexibility, as well as a good electrical flexibility. So with our solution, you can easily stack up between 1 to 6 power modules, and therefore you can have a stacking in the converter output power. And so with our solution, we can provide a very good utilization of the silicon, resulting in higher system current based on a really excellent current sharing. This will be underlined with some details on one of the upcoming slides. So with our solution, you can achieve a consistent switching performance for up to 6 modules in parallel. There is almost no difference if you operate 2, 4, or 6 modules in parallel. From a mechanical perspective, as I said, we are providing a high design flexibility thanks to repeating the approach from SCALE-iFlex. So we have the IMC, the master control unit, sitting aside from the modules, and we have the module adapted gate drivers sitting on top of each and every power module, easily scalable with the cable connection, and therefore supporting either air-cooled designs or water-cooled designs. So regardless the pitch between the modules, we can address this simply by using the same gate driver hardware. An important safety feature we are providing is called advanced active clamping. This feature helps to reduce the overvoltage spikes which are induced by the DC-link loop inductances. And with our solution, we enable our customers to operate the devices safely even with a higher nominal DC-link voltage, because we can control the voltage overshoots. So there's no derating needed compared to conventional design, which may otherwise be required to consider a certain high DC-link loop inductance. We also made investigation for this one, underlining the performance of our advanced active clamping. You will see this also on one of the coming slides. Now let's have a look at the propagation delay mismatch between paralleled power modules. So therefore we made an investigation with a 4 times paralleling approach. Therefore, we collected more than 500 data points under a typical application condition of 5 kHz switching frequency. And here in this table, you can see that we measured this for turn on and turn off commands for both channels, so INB and INA. You can see that the signal itself is transferred always within approximately 2 microseconds time frame for a turn on command and 1.4 microseconds time frame for a turn off command. And looking at the variance between the different power modules, you can see that the variance is within a 20 nanoseconds range. And this is ensuring an excellent current sharing. Because of this very low variance, we are making sure that all modules are turned on at the same time, and therefore they are carrying the same load current. To underline how accurate our current sharing is between paralleled power modules, We have made an investigation which you can see here. So for this, we operated 3 modules in parallel with a nominal current of 600 amps, which you can see here as the load currents IC1, IC2 and IC3. So we turned on all those devices and then we measured the current imbalance in steady state condition, and you can see that the imbalance between 3 modules is within a range of plus minus 20 amps. We have made this investigation also with 6 pieces in parallel. We are not showing it here simply because of simplification reasons, but also with 6 pieces in parallel, the imbalance is within the same range. Now I'd like to show you how our advanced active clamping is working and how it can control overvoltage conditions during turn-off events. So for this we made a comparison where we made one setup with a low DC link loop inductance design. So here it was 40 nanohenry, and we also compared it to a high loop inductance design. So let's start with the 40 nanohenry design. You can see first of all there's the IC, so the load current, then there's VGE, the gate emitter voltage, and there's VC, the collector emitter voltage. So the device is turned off, the IC is consequently dropping, so the load current is going down to 0. The VCE, the blocking voltage or the DC link voltage, is increasing. It is reaching a certain threshold, which is preset in our design. So this threshold is reached, our advanced active clamping is becoming active, and we are limiting the voltage overshoot. In this particular case, we had limited it to 200 volts overshoot compared to nominal DC link voltage of 860 volts, leaving more than 10% margin to the absolute maximum rating of the device, which is in this particular case 1200 volts. From an application condition, I would say this is the easy application or the easy control. Looking at a more challenging case, so here we made the same investigation with a loop inductance of 170 nanohenry. Again, you can see there is the load current IC, so we are turning off the device and therefore IC is dropping, VC is increasing, reaching again a certain threshold, and then our advanced active clamping is becoming active, which you can see in the VGE, so the gate emitter voltage. So there you can see that our advanced active clamping is actively again turning on the semiconductor to dissipate the overvoltage and turn this energy into heat. So we are thermally using the semiconductor to bring down the voltage. Again, here the overshoot is within a reasonable range. So here it was a 220 volts overshoot, still leaving 10% margin to the blocking voltage absolute maximum level. Looking at the scope of supply for SCALE-iFlex LT, you can see here in these tables how we will roll it out into the market. So we will achieve a full production release by end of 2021. We will start with gate drivers for modules coming from Infineon in both a 1200 volts and a 1700 volts voltage class. And soon after we will extend the portfolio to gate drivers to operate modules from other vendors such as Mitsubishi, ABB and Fuji. If you're interested in more information about SCALE-iFlex LT, SCALE-iFlex or any other power integrations products, please look at our website power.com.